Welcome back. So we wanted to understand how would our analysis change if we used a small compressor, which is another way of saying how would our analysis change if the mass flow rate wasn't constant, because again, maybe my compressor couldn't keep up with the supply that was required, or if we drained a tank. So let's say the pressure within a tank was decreasing as a function of time. So the state conditions and the mass flow rate could be changing as a function of time. Well, as we saw before, this transient analysis is pretty complex when we have steady conditions from our filled chamber. If they're unsteady, the analysis is even more complicated. So let's take a look at the specifics. So if we have our conservation of mass equation, recall before we had the change in the mass and the control volume from the initial to the final state was given by this expression for the mass flow rate into the system here. So what we need to know, again, is how does the mass flow rate vary as a function of time? And for this, you'd say, well, let's take the draining tank example. There, you would expect the mass flow rate to decrease as a function of time, probably exponentially or asymptotically. So you might imagine where the mass flow rate did something like this as a function of time. And we would have to decide, before we did our analysis, where am I on the slope? What's the magnitude of the initial mass flow rate? So this would be at, let's say, at the start of the fill, and this would be the mass flow rate at the end of the fill. And the same type of approximations we were using for the specific heat, when we wanted to invoke assumptions of a constant specific heat, we would consider here. For example, let's say if we're only filling for a very short period of time, maybe I can assume a constant value for the mass flow rate, and it's just an average between, let's say, this initial T1 and this initial T2. On the other hand, if it really is something, if it really is conditions that span from this really high mass flow rate at the initial point to really low mass flow rate at the final point, I might need to do a polynomial fit to that process. I might want to do a piecewise linear, but you can imagine you now have to take that information and you need to integrate it in this expression. Now, the next step would be then to consider the conservation of energy, which is also affected by a non-steady state condition within the fill chamber. So remember before, we said during the fill process that the change in the internal energy in the control volume was balanced by the enthalpy from the fill chamber and then the mass flow rate in. Well, in these conditions, again, doing a little bit of simplification here, from the initial state to the final state. So this would now be, integrated over a function of time, T1 to T2, and you could potentially have two variables changing simultaneously as a function of time. So the state within the fill chamber could be changing, and typically we would say, okay, we'd look at how the enthalpy changes as a function of temperature. So how does the temperature within the tank change as a function of time? And we'd have to have that convolved with the mass flow rate changing as a function of time. So you can imagine these get very sophisticated, these transient analysis with not just time varying within the control volume, but these fill problems or draining tank problems also become very complicated when we consider the system to be changing during the process that we're concerned about. Okay, so again, we try and design the systems or interpret or make assumptions that make them as simplified as possible, make them tractable. So when you consider transient analysis, try and invoke appropriate assumptions so that you can make the system analyzable, so it's tractable. You can do the analysis without overstepping or overreaching the assumptions. You could also consider limiting cases. Choose a constant mass flow rate, but the highest mass flow rate. Choose a constant or assume a constant mass flow rate, but the lowest mass flow rate. And those can bound your solutions. So those are all sorts of methods that we can use to make the system tractable for our consideration. All right. So we're pretty empowered right now. We have thermodynamic state relations at our disposal. We have simplified models. We have like ideal gas model, incompressible substance model. We have the two most powerful conservation equations, the conservation of mass, and the conservation of energy. So let's take a step back. There's another really critical application for thermodynamics, which is power generation. So that's typically either stationary power or power in the mobile sector, so transportation market. And we want to see how those systems are analyzed and considered from a thermodynamic standpoint. So the first thing we're going to consider are power cycles. And cycles have some pretty unique features. And let's start with those. So these are generic features of cycles. A cycle, by definition, has the initial state equal to the final state. So we'll write that down. By definition, a cycle ends where it begins. That sounds very philosophical. What we're saying is that the initial state for a cycle, thermodynamic state, is by definition equal to the final state of the cycle. Okay, if that's the case, let's consider some power generation, a power plant, or doesn't matter if it's a stationary power plant or a mobile power plant, like a diesel generator or diesel engine. We both consider them from this perspective in the same way. Let's look at that system and consider the application of the conservation of mass. So, conservation of energy for that system. So the conservation of energy, we're going to assume it's a closed system, a closed power cycle. And remember, in its most general form, the conservation of energy says the change in energy is equal to the heat transfer, the net heat transfer in, the net work transfer out of the power cycle. So this is generic for any closed system. Now we can just add subscripts to say, hey, this is specifically for a cycle. And we look at the definition for a cycle. Well, heck, the initial energy and the final energy of the cycle are by definition equal. So that means this is true. And we look at the right-hand side of the expression for the conservation of energy, and we say, for cycles, by definition, the net heat transfer has to be equal to the net work transfer. This is a statement of the first law of thermodynamics. It is always true. So as long as you can define a system as being a closed cycle, this is a statement of the conservation of energy, and it has to be true. It doesn't matter what the fluid is. It doesn't matter what type of power plant it is. It's always true. It's a statement of the conservation of energy. So again, always true. All we have to do is make sure that our system can be described as a cycle, and it does indeed have the initial state equal to the final state. Okay, so that's the generic description of a cycle. There are essentially 3 categories of cycles, and it's more like 2 categories because 2 of them look a lot alike. So in power cycles, the goal is to actually generate power or a rate of work transfer out of the cycle. The other flavor of cycles are refrigeration and heat pump cycles. So the goals of those cycles are actually to move heat around, to move for heat transfer, so to provide a particular type of heat transfer rate. So under the power cycle category, our goal here is to provide net work transfer to the surroundings. Okay, and the generic power cycle, or which is also referred to as a heat engine, and we'll explain why a little bit later, why they're called heat engines. But for power cycles, we just set them up for our initial conversation as being some generic, some arbitrary system, and that system is supplied with heat transfer from a high temperature reservoir. So we have heat transfer that goes from this high temperature reservoir into our power system, into our power cycle. And we generate work. That's the goal of this cycle. And of course, we're considering this analysis from the viewpoint of where the power cycle is the system. And that power cycle has to reject heat to some cold temperature reservoir. So this is a high temperature reservoir, and this is a low temperature reservoir. Okay. Now I can tell you that every power plant that generates stationary power electricity fits within this category. There are some very small fraction that don't fit within this general description, but the majority of them, over 90% of them, look like this kind of generic description. And the only difference between the power plants, whether it's a solar-powered power plant, a nuclear-powered, a coal-fired, a natural gas-fired, is in the details. But they all have the goal of generating heat. That's this high-temperature reservoir. So in the coal-fired power plant, we're going to burn coal, and we're going to use that to heat a working fluid. So our working fluid is within this box here, and that working fluid is going to then generate power. So let's be even more specific. Let's take our natural gas. Natural gas is a relatively clean burning fossil fuel. So we burn the natural gas. That provides us with heat. We use that heat to heat water, and then that water goes from a liquid phase to a vapor phase. And that vapor phase has a lot of energy, internal energy associated with it. We saw that when we looked at our turbomachinery analysis, and specifically steam turbines. So I take my liquid water, I heat it with the heat from the combustion of fossil fuels. That takes it to a high temperature steam or high temperature vapor. That high energy vapor is then expanded through a turbine. The turbine spins a shaft, and out of that shaft we connect it to generators, and then we connect it to the power lines, and that gets us power out into society. Okay. We know that as we move that steam through the turbine, we go from a high energy state to a low energy state. And then we want to close this loop, so we take that low energy vapor and we condense that into a liquid. And in order for us to condense the water, we need to remove heat from that working fluid. And that's this portion of the power cycle. So we reject heat out of my power plant and into some cold temperature reservoir. Okay, so that's the generic description. I gave you the example of a natural gas-fired steam cycle. And we will go through the details of these cycles. That's what we're going to spend some time on in the next few segments. What I want you to think about before we come back is, where would a nuclear reactor fit in this little description of a power plant? So what does the nuclear reactor do, the actual nuclear reaction itself? And where would we kind of plop down that nuclear reactor in this little schematic diagram? So that's what we're going to start with next time.